Okay, let's get started. Thank you all for coming. I wasn't aware there was so much people interested in the way we try and do things here at Tradeshift. I see a lot of people at the door even, but we'll try and make it as comfortable as I can. So my name is Ypma. I'm a developer at Tradeshift. I'm currently working a lot with event sourcing and trying to build systems that way and evangelize a little bit on how to build systems that way. I'm also a contributor to the Akka project, which is a lot of the technology that we'll be talking about today. I'd like to start a little bit with the history of Tradeshift, and then mostly on the technological side that sort of led us, and me specifically, to evaluate this kind of building systems as opposed to more traditional approaches. And then we'll go a little bit into the implementation part and see how the different parts of mostly Akka plug together to achieve the kind of systems that we want to build. So back in 2011, when I joined Tradeshift, the architecture looked pretty simple, like any of you have seen before. We figured, okay, by the way, Tradeshift is a platform for business-to-business transactions that has a worldwide network where businesses can join and that they can interact with other businesses. It started off as an electronic invoicing platform, but we've built a lot more around the processes that go before and after invoicing. But at its core, it's really about exchanging legal documents between companies. And with the way we set that up, it was mostly Java developers at the start. As well, we have a backend built in Java and Spring. This talks to a standard old Postgres database. There's a front end we originally wrote in Grails because that was hip at the time. And I did all the UI work, and we had sort of a multi-tenancy thing going on where each customer on the system has its own slice of the database, and we figured, well, once we grow out of the one Postgres, we can just create more users on the new one that we would start, and everything will be fine. What else could we possibly need? So back then we had about 10 developers and maybe 1,000 companies signed up. And so most of these are just small businesses, like one business owner, just one individual doing some invoices. It was not a particularly high load. As it turned out, the business idea worked because we fast forward to where we are now. We kept on hiring new people, building more stuff, growing into new businesses, finding out that Denmark, where we started, was not what the whole world looked like. So we got some things wrong and had to revisit a few things, and also had to, because we had more people, build some new systems so that people could work more independently. And I tried to give you a nice picture of what Tradeshift looks like right now internally. Turns out it doesn't look that nice because I was writing arrows with all these dependencies, and it kind of reflects what we go through on a daily basis, which is that our old backend just basically turned into the good old monolith of where everything started, and nothing really got ever taken out because there was no short-term benefit of doing so. So now we have a lot of old complexity tied up in here that can't really move anywhere without some big changes. So something needed to be done there in scaling that up. The thing, though, is that while we were growing load-wise, we found out that Moore's Law, which I suppose you all know, also applies to the biggest server that you can buy on Amazon. So as the number of companies that we needed to serve grew, the biggest server that we could run our Postgres database on also grew. And we could still support all those companies in our one database. So the original thought that we had, and when we need to scale up, then we'll just create a new database and a new stack, a new shard with the new customers on it. We didn't really have to look into that. Unfortunately, that's kind of the side effect that nice tenant isolation that we started out with as an architectural principle turned out not to actually be there in practice. And there are a lot of features that, because it's all one database table, still cross-join and bind tenants together in ways that really ought not to be done, but it kind of works because they're all there in the same database. And that's a bit of a mess that we're currently in. Another thing is that because of the complexity that increased and the new system that we ended up building, failures started to be much more frequent. And not failures because of the number of servers that we had. We didn't have that much, but just failures because we changed something here that affected something else where the people didn't really expect, or this functionality was kind of built and finished and it worked at that point in time, and then you change something later and there were not really anybody taking any care of that, and it just breaks as a side effect. one of the results is that our operation guy said, okay, we can't have these services going out of memory or crashing inside a deadlock of threads anymore. We want at least 3 copies of everything. So all components need to be clustered. And writing something to be clusterable is something that is a solved problem. I mean, if you write something new, you know how to do that. But again, the existing components weren't really written in that way. They were assuming a sole ownership of some things. So something needed to be done there to come up with a sort of an alternative approach. But we weren't just scaling up in the number of users. We were also scaling up in the number of developers and the number of offices and the time zones that the offices are in. And we still needed to the world look like one platform. So it's not like we could just build different things altogether. Where in 2011, if you were to look at the skill sets in Tradeshift, it's really mostly a Java shop. People are hired if they know Java, and then we can work, and that's sort of the language that everything was fallen under. But it turns out there are good language choices to solve particular problems, and Java is not always the most obvious choice. So we've diluted a little bit from that, and finding out that in certain domains there are a lot better choices or more natural fits for certain things. That some of them fall inside the Java realm, some of them are a little bit outside of it. But we came to realize that if you actually want to scale up your organization, it works best if you have the teams being able themselves to decide what to use. And we're still mostly a Java shop, so people often use Java to build new things. But Scala and Node.js and other alternatives are very often picked for new projects as well, and that's something that should be encouraged. But it does mean that you can't really limit yourself to one framework or one architectural style. Now, I wanted to zoom in on one particular failure that has brought us down a fair bit of time ago now. So one way that you can use Tradeshift is through the web browser. And in this particular example, there's the user wants to view an invoice in a particular language. So through a public API proxy that sits there, they call our backend, which finds out, okay, and an invoice needs to be rendered. It calls the front end because it's sort of the rendering is UI work. That's how we decided that the front end is supposed to create the HTML that's then turned into a PDF. So the backend calls into that. The front end doesn't have all information, so it has to call back to the backend to fetch some additional things. And then we have a sort of a plug-in mechanism called apps, where certain third parties and partners can put additional code in our into our deployment, so that we can do extra validations or some customizations that they want. That's where it all went wrong, because that ran some queries on its own database that caused it to behave fairly slowly. Now, at this point, we have like 5-6 threads just waiting on each other, and nothing is really happening. And the database is just struggling to get the answer out. So what does the user do? Well, psychological tests show that after 1.7 seconds, the user will press the reload button and try it again because it didn't work. Our threads don't know that. They'll just sit there and keep working. So that just goes horribly wrong. So we need a way to somehow isolate these problems from each other, because the fact that this particular plugin mechanism is not feeling well shouldn't really affect users using other things on the side, on the site. And we should be able to better zoom in and say, okay, if this goes wrong, nothing to do about that, but let the rest continue. And over the years, a lot of people, of course, it's not the first time this problem comes up. A lot of people have looked into, okay, how can we isolate failures, and how can we build distributed systems in a way that we get more predictability and more resilience against errors. And to me, it started a little bit when I discovered Erlang and Joe Armstrong's description of how the actor model has helped Ericsson to build systems with very high reliability. But from there, there have been a lot of approaches to try and zoom in and make more specific, okay, what kind of techniques can you apply to build a distributed system that does not go down as easily if you start poking around and tease it in the wrong way. The most specific one I've come across is actually a recent description by, I think, a few Germans. I forgot exactly whom. But the architecture styles, they call themselves self-contained systems, and they kind of took the somewhat vague definition of microservices, which doesn't say much more that it's a service and it's small. How small, everybody has a different opinion of, what you specifically do. But they made it a lot more concrete and say, okay, this is how you actually build these services. So, and I'd say the 4 of them has really affected the style of architecture that we're implementing. So what do they say within self-contained systems? Self-contained means that if I'm system or service number 1, and I get a request from the outside world, I'm not allowed to talk to any other services in order to answer that request. Seems a little boring, but it implies that, how do I get the data? That I have to replicate the data in from service to asynchronously to me. And then only the part of the data, of course, that I react on. So rather than when I get a request for, refer back to our keynote, like what channels can I view, that then I ask some other service, hey, what channels are available, and they come back and I send them over. Rather than that, I should have a copy of the parts of the channel that's interesting to me in my own data store that I picked and that I trust to answer that in the kind of queries that I want to run, and simply get changes to those channels as and when they happen, replicated to me so I can apply them and eventually make that part of my response. Of course, there is some replication going on, but that's just one extra replication over the distributed replication you would do anyways if you are applying distributed database like Cassandra. So it's not necessarily a bad thing. And very often, if you choose your boundaries of your systems right, you're not copying 100% of the data from A to B. There's only a subset like a search index or something else that you have to build, and for that you don't need to store the whole source of the data. So that's what self-contained system says. On top of that, we also said, okay, when you build such a system, there should not be a single point of failure. So if you build a service, you have to add your clustering and some other things to it to make sure that if a node goes down due to hardware failure, that the whole thing keeps operating. But then there's also the load question. So if you design your system and you build it in a certain way, you should have an idea, okay, how many of X can I handle? How many concurrent requests can I handle? How many users can use the system? How many users can I store in my data store before it goes belly up? There are a lot of questions that you should at least have a gut feeling for and preferably have tested so that you know, okay, we're trying to implement this business feature. We're expecting to get 10,000 customers this year, but if we were to get 100,000, I don't have to revisit my architecture yet. And that sort of that extra thought is very important when, at least in our context, where we're effectively still a startup, where we want to do sort of just enough to serve the need of the customers that we expect to get, but then still, if a feature is successful, to be able to keep rolling that out while we revisit it and make sure that we know when we need to revisit it going forward. Because we found ourselves historically a lot in the situation that we had a feature that worked functionally, but then as soon as 2 people used it simultaneously, weird things started to happen. Somewhat embarrassingly, I'll admit that we even had a bug where 2 users, if they requested an invoice at the same time, they would actually see each other's invoice. And yeah, that sort of thing, you hit once your load hits a particular amount, because the likelihood that 2 people, even if you have a fair amount of customers, that they do the exact call at exactly the same time, actually isn't that high, because calls tend to be fairly small, and if your system is working well, then they don't occur that much. So the advice there is think about your load and be specific about what you can handle. But zooming in more to the architecture I want to talk about today, I want to talk a little bit about event sourcing, which uses events in the same way I think you've seen them in the keynotes, but the tweets coming in and some other things that might have happened. But in event sourcing, events aren't the side effect that happen because of what your system is doing. So if you do event sourcing, it's not like, oh, I stored a document and I made some changes, and as a result of that, some events are emitted. It's actually reversed. In event sourcing, as you make changes to the document, you look at what your state is, and if you decide to emit some events, then as a result of that, you update your state. So the events become the single source of truth in your system, and everything else is a side effect of that. And if you have a traditional Postgres database model, you can still have it, but it would be a side effect of the event. So rather than request coming in, I change my Postgres database and something is emitted, you say a request comes in, I evaluate the request, and if I like it, I emit the event, and as a result of that, I update my Postgres database. And it has a few advantages that we'll get into. I sketched a small example here on what a particular event sourcing system looks like. There's a little bit of a pet shop or pet registration example where you have a couple of different users, and they can use the system to register the pets that they have, maybe to order automatic food or similar things. And we have user number 1, which was created with the name Bob, and a little later, a new user is created with the name Alice. And first, Alice registers a pet. A pet was added called Gary the goldfish. Sometime later, user number 1 also registers a pet, Charlie the cat, and miraculously, after that, Gary the goldfish disappears. So you see a bit of a timeline in here. Certain events happen after the other in real time, because that's also how it happened in the narrative. But within event sourcing, the only guaranteed order that you're going to get is the order within one user. And that means that if you look at the event stream, you can make conclusions based on the ordering of events within that user. So saying, OK, I know the user was called Bob before he registered the cat. And for user 2, OK, I know that the name was changed to Alice before the goldfish was registered. But you don't know for sure that the goldfish was registered before the cat, even though your timestamps may say so. Because let's imagine some actual timestamps in here, right? And let's say they're in milliseconds, and let's say that this timestamp is like a full 10 minutes before this one. Then it's probably fairly likely that in reality, the Gary the goldfish was in fact added 10 minutes before Charlie the cat. But what if our server clocks were drifted and we were not running NTP, and the clock was sort of a full 10 minutes behind the other server? Then your events will say that they're 10 minutes behind, but it could very well be that in reality, these two users might be sitting right next to each other, and one of them added it before the other. So the likelihood of a 10-minute clock drift is not that high, so this one I would put on the likelihood of saying, OK, it's very likely that they in fact happened before each other, but you don't know that for sure. And those are things to keep in mind, because with event sourcing, you deliberately choose to say, I get no guarantees on ordering between my aggregates. The user is an aggregate in this case, which is fairly close to the domain-driven design term. And for some domains, that's OK. For some domains, it might not be, but it's something to keep in mind. What you, of course, can do is say, well, I'll just look at these timestamps and do with it what I feel like. And if the server says they were before each other, I'll just treat them as such and show them in the user interface as such, because often it doesn't matter that much which one comes first, as long as, while you present it, you always show the same one first. And that, of course, you can do, because you do see the same timestamp every time you look at it. If you do need to reason about something that spans more than one aggregate, so more than one user, what you can do is you can create what's called an event listener, which is something that will plug into the complete stream of events for the whole system, and then draws conclusions from that. So, for example, it could look at changes to users in the Copenhagen area or in the London area. It could look to changes to pets that are fish or pets that are cats only, and that way, say, I don't know, create a search index, or update a database, or even maybe pre-render some HTML for this particular user's homepage. And sort of all kinds of changes can be materialized out that way that don't necessarily have to be within one aggregate. Now, event sourcing as an architectural style and as a data style isn't that new. If you've ever used a bank account, those are all event source systems, because they store changes to your balance only, and then the current balance that you get is just by going through those events and calculating out what your current balance is. But traditionally, the stream of events that happens in such an event source system is not exposed as such. You might have an API that says, get me the history of my bank account for today or for yesterday. Or you might have a call that says, give me the latest 10 changes or something, and some pagination. But it's not that often that you can get sort of a streaming protocol for the events themselves. There's some reasons for it, because you can promise a lot less consistency, like when are you going to see those events and in what way. So there's some semantics to be figured out. Security is another thing, because remember when I said, OK, you get this event listener and it looks at the whole stream of events, that means it sees all data for all users. So that means that whatever security you had on your API on system 1 you have to make sure that system 2 at least upholds the same confidentiality and same restrictions. Because if you send all your data to system 2 and then they make it available to the world, that's obviously not what you want. So it moves some security around in ways that are not unsolvable, but you do need to keep that into account. So I want to look a little bit into the more technical side of things, since we actually have this running in production. And let's start with the actor model again. I already said that it was the first thing that inspired me to think in this direction. And it's the list. Let's do a quick raise of hands. Who of you have not heard of the actor model before? Okay, very few. Who of you have not heard of Akka before? Okay. Who of you have never written anything using Akka? Okay, so that's sort of the level where we are. So that's okay. So an actor is a little bit like a thread, in the sense that it does things sequentially, but what it does is much more restricted than a thread. The only thing an actor is allowed to do is receive messages and act on it, and then get the next message and act on that one as there are messages, and when there's nothing to do, it'll go to sleep and not do anything. But because of that restriction, an actor is much more lightweight than a thread. Because you know when it has worked, that's when there are messages. You don't need to keep a stack around for it while it's sleeping. So in a typical actor system, you can have millions or even more of actors, while you wouldn't have millions of threads. I've never tried that. So if you use Akka, an actor is just a normal Java class. You extend a base class, and that makes it an actor. And then, of course, you get to implement a method that says what to do when you actually get a message. Messages themselves are also normal Java objects, but because of the asynchronicity of sending a message, meaning that when you send a message, you don't wait for that message to be handled. It is a little bit like putting something on a JMS queue or to RabbitMQ or any kind of queuing system, where you put the message in, and then Akka says, OK, thank you, I will eventually deliver that. But you don't really know when that is or if it even gets delivered in some cases. So that's something to keep in mind. But it does mean that as long as you send that message, that you shouldn't go around and change the contents of that message as it's on its way. Of course, you can't do that for a message queue because it kind of leaves your system. But these actors, they are within the same JVM, so nothing would be stopping me to create a Java object, set it on its way, and then 5 milliseconds later, go ahead and change its content. It would be a bad idea because the other actor that's processing that message might be running on a different thread, and generally you want these things immutable. Serializable as well, we'll get into that because the other actor might actually be across the network on a different machine. And that's nicely transparent to you as a user. It's one of the big benefits of Akka. But one important thing that you also get is that the actors, they're not created willy-nilly where you say, OK, let an actor here, actor here, actor here, and I have a big cloud of them. The actors actually structured as a tree, where you have in the actor system, the collection of actors, you have one root actor where everything starts. And you can create leaf nodes of that root actor, but it's much more customary to create an actor that sort of covers what you want to do and then create sub-actors as a part of that might create other child actors to do work for them. So if you need to delegate something out, a very common pattern is to create new actors to do stuff for you. And there is an error handling mechanism in there that scales very nicely along those same boundaries, where a parent is responsible for basically cleaning up the mess that any of the children might cause. I might recognize that. I have one child myself. But the way that works is if an actor makes a mess, and that's defined as throwing an exception while handling a message in its message loop, what actually happens is that the actor doesn't get to say anything about that. It's always the parent that gets to decide what happens. What happens by default is that Akka will restart the actor, meaning that a new Java object will be created according to the same recipe, and new messages will be diverted to that new object. And it has to do that because it doesn't know what went wrong. Imagine your standard Java object where you invoke a method, and a method throws an exception. Say it's an illegal argument exception. What would you do afterwards? Would you want to reuse that Java object? Maybe you do. You said it didn't like the argument, so probably it checked it before it mutated any state, and I can reuse it. But maybe it didn't. Maybe it updated a cache and then found out that it didn't work. So it had actually changed its state and then thrown an exception. And if you then go and reuse it, you might get something corrupt. And since Akka can't really distinguish between those cases, the safe default is if your object throws an exception, it gets thrown away, new one goes in its place. You can change that if you know, okay, I always store illegal arguments exception in the beginning, so you can reuse it safely and do something else. That's all fine. But there is another effect of this, and that is that since it's always the parent that handles the errors that the child does, if there are other actors communicating with the same child, they are not involved in error handling. And that's very nice, because it means that if you're communicating with an actor, say you have an actor abstracting your database access, for example, and you can send a message and say, read some rows from my database, and call me back when you got them. And you have, say, maybe 50 HTTP requests all asking stuff from that actor. If the database goes down, and maybe the actor crashes as a result, it's only that actor's parent that needs to take action. Maybe the action is to restart it or to wait around or do some repairs. But all the 50 clients, you don't need error handling code in there. They can just keep sending messages as they're used to, since the endpoint will do something sensible with it. And I find that sort of a very nice paradigm to be in, because it helps you from duplicating out error handling. And of course, in the Java frameworks that you know, you can centralize your exception handling in one place, but the exception still goes through all the parts of your code, and maybe it's not caught or somebody catches it and does something else. It's not always the most natural path for an exception to go all the way back to the surface. So I kind of like the isolation there. And of course, it goes back to also to say, okay, let's isolate the errors where we can. And in this case, it's just the one actor. I want to show a little bit of code on what writing an actor in Akka looks like. This is how you would write one in Java 7, where you extend a base class called untyped actor. And we're going to write a little system called actor ping pong, where there are two actors and they exchange a few messages, and then the example ends. So this is one end of it, where whenever it receives a message, if the message is a string, it will print something and then send a pong message back. And there are a few things to discover here. One of them is that the onReceive function takes objects as a message, which means that you don't know what you're getting. It also says untyped actor at the top, which means in Akka, messages are untyped. And it has advantages, has disadvantages. The disadvantage, of course, is you don't know what you get. But the advantage is that you can extend your protocol in such a way that you can just ignore messages that don't make sense to you. Say you're acting as a proxy for some other actor, and you only want to respond to some parts, you can simply do that by Java typing and say, OK, this message was for me, and the other message, I don't know what types they are, so I'll just send them on to my delegate. And patterns like that are fairly easy to code in Akka, because you can send any message to anywhere. And if your method doesn't handle it, you can simply ignore it. That's fine. Another thing you might see is that while handling a message, I have a reference to the sender of that message. So while handling a message, you always know which actor sent that, which also means there always has to be an actor sending the message. And you can use that reference to send something back. That's very useful, because then request reply and some other mechanisms you can write directly. You don't have to encode the sender into your message yourself. This is the other side of the example, which initiates the system. And this one I've written using the new Java 8 variant of writing actors, where they introduced the DSL to make the matching on particular message types a little easier. Since in this case, our actor acts on two kinds of messages. You can send it a string, or you can send an instance of initialize, which doesn't contain anything, but it's just a Java type that I made up to say, start and go and do your work. Now, if you had to code this using the Java 7 variant, all you would get is an object. So you would have to write something like, OK, if it's an instance of this, then cast it to this type and do something with it. And if it's an instance of this other class, then cast it to that and do something with that. But with the receive builder DSL, it becomes a little easier, because all I have to say is .match some Java type, and then Java will infer that this argument to this lambda here is actually of this type. So I don't have to repeat that type twice. And that's fairly nice, because then I just have to spell out once, OK, I can handle initialize and do this. I can handle string and do something else. And that saves a bit of tedious coding. So what actually happens in this particular actor is that when it's constructed, it has a field called a counter, which holds the number of messages received. And we also create another actor. So this is an example of how you create a child actor. You can create a child actor using the actor_of method, which is curiously not named create actor. That's a historic thing. I don't really know why. But this does always create an actor. It's not like a lookup thing that would return an existing actor if it exists. It will fill if it exists. So They might consider renaming that. But what you pass as an argument is not maybe what you would have expected, an instance of the Java class you want to run. Rather, you give it a recipe, a factory of how to create that. And the reason that you don't pass an instance, but you pass a recipe, has to do with the restart and the error handling behavior. Because Akka has to be able to, if the actor crashes, to create a new one in its place without calling back to you or do something other. And that's where that props class comes in. So props will handle the props is like a factory for the inner actor instance that's actually running. And then you give it a name as well, which helps with debug logging. All the actor names go into a nice path separated with slashes. So if you do logging from the actor, you know exactly what instance is doing stuff. And then when we receive the initialize class, we just send the first string to the pong actor. And when we get a string, an instance of string, which hopefully is the string that the pong actor sent back to us, we increment our counter, and after a few messages, we shut down the whole actor system. It's a little bit equivalent to system.exit for plain Java. And no, you wouldn't do that in a real system. But otherwise, we send the ping message back again. One thing to take away from this maybe is that the counter here is just a plain old integer. There's no synchronized or atomic integer or something else, even though the actor might handle its subsequent messages on different threads. But still doesn't have to be synchronized, because Akka will guarantee that an actor will only handle one message at a time. So you can really think of an actor as a subsequent invocation of the onReceive method without there being any kind of re-entrance in that. So it won't be invoked on the same thread, but it will not be invoked more than once. And that means that within your actor, you don't have to synchronize on anything. That also means you can get quite a bit of performance out of it. Now, if you were to run all of this stuff, you get some messages out. This is just how you would actually put the whole thing together. There's not that much more involved, except that you have to create an actor system, which encompasses the runtime that the actors can run in, like the thread pool and some other stuff that needs to be set up. And then the way you create a root actor is by saying system.actor off, because you don't have another actor to create it under yet. And then there's a similar props, just like the other one, where you say, OK, now I want to create a ping actor. So that's just actors, which are nice to build certain asynchronous patterns on, but they don't really relate directly to the event sourcing and all the distributed nature that we talked about before, because they only live in the JVM. They don't have any persistence. If you reboot the JVM, all your actors are gone, and you have to create them again, and all your state will be lost. But there's something to help with that, because Akka comes with an event sourcing framework called Akka Persistence that uses event sourcing to help you reconstruct the state of an actor after it comes back after a restart. And you can store stuff in a few different databases. But what you have to do is you extend a different base class, in this case, abstract persistent actor, which is still an actor. You can send it messages, and everything we talked about still applies. But it's also persistent. And it's persistent using event sourcing terminology. I'll go into a moment into what that actually means. But for the demo purposes, I've extended this a little bit to the use case of a chat application. So imagine that we're writing something where people can, in real time, exchange messages with each other, like Slack or any of the other examples. And we want to do this using actors. Then our chat actor probably has a list of messages, which is the current list of messages in this channel or this particular topic that's being talked about. So that's just a plain old array list. And let's introduce a few private methods that help us deal a little bit with actions that might be performed. One of them that might occur is that a message is posted. So somebody is sending us a new message in the channel, which inevitably we want to add to our list. But we also want to remember that that message was posted. And to remember something is calling the persist method. So persist is a protected method on abstract persistent actor that will persist an event. And the events are the things that you saw on the event sourcing picture, like the boxes that say this changed, this changed, this changed. In this particular case, our event is just a string that says a message was posted. But in a typical system, you would model like some actual concrete events that tell what was going on. So we persist a string. When that is done, so there's a little callback here, which Akka will invoke after the journal has says, OK, I've saved this. I promise you it will come back if you restart. Only then do we actually add it to our list of messages. So this actually means that the other users don't actually see the message until it's actually safely saved in the journal. And then we send a reply back to the original sender, because we still want to inform our client when are we done saving this particular message. Because if we have like a typical HTTP REST API, we still want to send a 200 OK or something after we're done saving it, so the client also knows that the journal promised to store that message. So that's posting. Then the other side of the equation is people might want to get the current list of messages to find out what's actually being talked about in the channel. That's fairly simple. We just send our array list that we have to the sender. But we can't actually send the array list that we have, because that's the thing that we are mutating. Remember, array list is a mutable structure. If I say list.add, it will actually add a new element to it. So if we were to send that as a message, we would send a pointer to our internal array list to the sender. And then after that, if there are new messages coming in, they will be appended to that array list, which would at least not be what's expected, but it will probably cause concurrent modification exceptions and all kinds of other weirdness, where sort of halfway along your interpretation of that array list, messages are being added or deleted. So we send a copy instead, because then you know, okay, that object is immutable, it can no longer be changed, and then the sender can do with it as they please. Now, in order to get it to fully work, we have to implement 3 methods that Akka dictates. One of them is a method that returns the persistence ID for this actor. It's a unique identifier that the journal will use to find the events for this particular actor again later. And usually it's not a fixed string, because then you can only have one of them. Usually you tie that either to something you get into your constructor, or you make it equal to the actor name, because that's also something that needs to be unique, and that usually fits quite well. But that's a string how you can find the same conversation or the same aggregate again later. Now there are 2 methods that you need to implement. Besides that, there's receive command, which I'll go into first. And that goes in place of the normal receive message loop. So you don't implement the default loops that you saw before, but rather than that, you implement receive command. And the reason for that is that there are some internal messages that are also handled by the actor while it's booting up, and they're handled in a different way than normal stuff that comes in. And receive command basically covers the normal stuff that comes in. So your external API to this actor, like which Java objects can I send to it and what do I do as a result, you would put in receive command so that the internal stuff is handled by Akka internally. The second method that you need to implement is receive recover. And that's one of the internal parts, namely, as the actor comes back during a restart, it needs to have a way to come back to the state that it was before. Because remember, all we're persisting are events. At no point, we have this list of string of our messages, but at no point do we actually persist the whole list of messages. Like, we don't take like a snapshot of our internal state or serialize the whole actor or something like that. Because that's not what event sourcing is about. Event sourcing is about serializing events and recording what was happened so that we can later on replay them and reconstruct our state. And that's what you're supposed to do in receive recover. If we skip over the syntax for a moment, what we actually do is that, well, whenever we find a string in our event journal, so whenever any of the strings that were persisted earlier come back, then we add it to our messages. And that makes sure that after a reboot, we go into the journal, we try and find all the string events that were persisted and build up our array list again. And Akka will guarantee that all of that will be invoked and will complete before we handle any new messages or commands that come in. So it will sort of queue them up, and they won't make it into our actor until afterwards. And it leaves receive command to then handle the actual API, like how can we talk to our actor? And in this case, I've made it only react to strings, but if you send it /list as a string, it will actually reply with the whole message list. If you send it any other string, it will consider that a new message to being sent to the array list. Now, the receive builder thing is here again, and what it actually returns is a somewhat scary signature of a partial function of object to boxed unit. Who of you know what that is? Okay, so it has a real reason and a made-up reason. The real reason is that Akka is written in Scala, and this is something that is a first-level thing in Scala. I can give you the made-up reason, which sounds a little nicer. A partial function is not something Scala made up. It's a mathematical term for a function that's only defined on some inputs. Specifically, this function is only defined for the string called /list and other strings, but it's not defined for an instance of date or an instance of vector or something else. And that's important knowledge to have, because in actors, it's fairly common to want to reuse certain behavior. Say that you've written a piece of profiling where you say, okay, you can send in a message, start profiling and stop profiling, and that's something specific. Now, the handling of that message is not something you can just make a method do, because a method in Java, you have to invoke it, and then it returns something. But if you just have the void on receive, and I'll try and find it back, like you don't know whether this method has actually done something to this message or not. So you can't really chain these things in a nice way. Now, you could have it return a Boolean, and then say, OK, I'm going to try this one, and if that returns false, then I'll try the other one, and then you can create some soup of chaining those together. But the partial function actually has a nicer way of saying, OK, try this behavior, and if that didn't do anything, try the other behavior, and if that didn't work, then try something else. And I personally would have made it a little bit more Java-friendly, if possible, but there are some merits to having it this way. So now that we've built this, we have our persistent chatting system, and we can imagine some kind of HTTP API on top of this. And it would work. I mean, if you reboot it, it will come back, and all the chat windows will still work. But if we were to boot it twice, so we have two servers that connect them to the same database to try out our clustering, or at least multiple deployments of it, it wouldn't work, because if we have like some load balancer on top that would arbitrarily send requests left and right, we might start to instantiate two actors for the same persistence ID on the two different servers, because they don't know of each other what they're starting up and who's handling what. And that's a bit of a problem, because the event journal and all the other code here is expecting there to be only one actor per database, or rather one actor per persistence ID per database, since there are sequence numbers and other things involved. And if two nodes start to create messages for the same persistence ID, they'll eat each other's sequence number. If you're lucky, the database will make sure that only one of them comes through, but it's not kind of the world you want to be in, and it really depends on the database and the implementation that you're using. What you can do instead is there is a way for an actor system to run across servers. And there's actually not that much that you have to do that. There's some hocus-pocus configuration that you put in, but that's all. Your code doesn't change. Your actors are still actors. Your references to actors are still references. It's just, if you now send a message, it might be messaged to an actor on the same server. It might be messaged to a different server. And that's really nice, because it means that all the mental models that you're learning while working with actors actually work for one server, but it also works for 200. Now, if we add remoting to our solution, there's a small layer on top of the remoting, which is the important part, and that's called cluster sharding. What Akka cluster sharding does is it can manage a pool of actors, which are typically persistent actors, but they don't have to be. And it can manage that on a cluster of nodes using a standard sharding approach, which is similar to maybe if you've heard the Cassandra talks before, where you say, OK, this group of actors goes over here, this other group goes over here, this other group goes over there, and if the server goes down, we reshuffle them in a way so that we can keep on working, and they'll come back somewhere else. And that's what the cluster sharding system does for you. For that, again, you have to implement a few methods, because what cluster sharding does, it presents itself as a proxy that sits between the actual sender of a message and the target actor that it might go to. And it needs the information to be able to say, OK, where do I need to route this message? And what shard is that? And then what node is that shard currently running on? But once you implement that, then all you have to do is actually boot up an instance of the cluster sharding extension, which you give a name. That's just the name that the actor will be. You give it the props of the actual target actors that it needs to create, since it will manage a pool of actors, and we need to tell it the factory to create those. That's our props object. There's some settings that you can just leave at default. And there's the custom code that tells you, OK, how do I do my routing? And after that, you can, instead of talking directly to your actors, you talk to that proxy. And if you do that across your actor system, then now you have to guarantee that your one persistent actor for each user or a document or whatever it is that you choose as your aggregate will only be present on one node in the cluster. And because those are persistent actors, if we shoot that node in the head and it goes down, we know what to do, because it's a persistent actor. All we have to do is boot it again on a different node, and it will come back and it will recover just like we already talked about. So that sort of gives us the final piece of the puzzle to build this distributed setup where we can now have the actors with their state and whatever it is that we want to do as plain Java objects, but Akka will make sure that lives on whatever nodes are currently available. So when we found out about the technology in Akka and learned it a little more, we figured, okay, this might be a very good fit for what we need to do, but it's kind of new to us and we don't really know if it's going to work. So let's try it out on a sub feature first. Now, accidentally, one of the features that we were going to add to our platform actually is exactly this, real-time chat. So we called it collaboration, but the ability to talk to each other about an invoice that people are creating, like, hey, I'm about to send this, can you give me some discount? And that kind of hip communication back and forth that says what we should do with it. So we built that using this architecture, and it's in production right now. I'll go to a little bit more detail what... actually, let's do that right now. So the collaboration stuff that we put out looks like this, where we have a content part, which is the thing that's written in Akka. So that handles the conversations, what happens to them, what messages are exchanged, and there's some other semantic metadata that happens in that. It's not only a text interface. But it's a plain Akka application that's written using the stuff that you saw, that runs on a few nodes, that stores its stuff in the Cassandra cluster. But it doesn't do any UI. The UI part is written by a completely different team in Node.js, and they don't know anything about Akka or any of the related technologies. They simply listen into the event stream, and they see, okay, messages are being added to these conversations, so we'll update the HTML accordingly using WebSocket or whatever makes sense in that particular browser context. And not only that, we have a different component, which is called our workflow system, which is what you expect, like a workflow management thing where an invoice goes through certain states. And they also wanted to have changes from that thing present in the user interface. That turned out to be fairly simple because you can always add, if the system is already storing stuff as an append-only, in an append-only way, you can just treat that like an event source. And instead of having one source of events, you just have two sources of events. And whenever anything comes in somewhere, you just update your state accordingly. And it was kind of a nice experience to go through that and see how these two different teams set it up and still are able to collaborate on it. So we're definitely taking the next steps on this. And one of the bigger things that I showed in the beginning, like the big backend, which is right now handling all of our document management, the next step that we're doing is actually coming up with an event-sourced way to represent that, so we can finally start to pull some stuff out of that monolith and hopefully also distribute the development a little better. There are some challenges, though. One of the things is that there's still a lot of development going on within Akka. Stuff keeps improving, but sometimes they also find out, okay, semantics that we kind of promised on the events here isn't quite what we thought it was, and there's some edge cases in Cassandra. And we use Cassandra 3's replicated views, or the thing where it's on its own will replicate some data somewhere in a slightly different setup. And that's also fairly new, and they may be fixing it up. So maybe there's some hiccups that we don't know about yet. But another thing is that as I talk to developers, some of them will sort of get it and find out, okay, this is one way that you can achieve all these things. And sometimes you need it, sometimes you don't, but they get it. But there's sometimes also the attitude of people that, okay, I know Spring, I know how I write this standard application, and I know it's only 50 or 100 threads, but it's good enough for me. Why should I learn something new? And I think in order to get people across, I think we need to show more success stories of this, because event sourcing is not something that that's like, oh, you might do that, and it would be nice if we had it. It's actually not that complicated a metaphor to get started, and you don't need to use Akka for it. You can do event sourcing in many different ways. So I definitely recommend you to try that out. I think that's it. Any questions?
We've been working with Akka for a bit, and one thing we've had a problem with here, I want to be able to see all the actors it's gone through. Have you come across anything that?
So the question is, in an actor system, like any asynchronous system, and maybe you've heard the futures example before, where that's also true, stack traces are not that useful anymore because one part of your system does something here that asynchronously triggers something here. In case of actors, it's a message, but it could also be a future callback. And then something happens here, and then something here, and then it blows up. And maybe the source of it was like a couple of futures back. You don't see that in your stack trace. And unfortunately, there is no real single answer to that. There are a few frameworks that you can use that keep some identifier across actor invocations, and Kmon is one of them. If you don't know it yet, you should definitely check that out. It's both a monitoring tool and a tracing tool. But in my experience, one aspect that you get with actors is testability. Of all the stuff that happens concurrently, you can now, rather than spinning up 5 threads and seeing, okay, does my handwritten concurrent list actually hold up to the stuff under use, you can now just boot up that one actor and send it some messages and see something comes out the other end. And reasoning about that becomes easier. So I'd say put a lot of stress on writing unit tests around the different parts of your system so that the likelihood that you get these big chunks of behavior that you can only trigger if you sort of hold it exactly like this and then kick it in the butt, that they simply don't occur as much. But of course, you have to deal with the stuff you're in. So adding traceability is something you can try that. Any other questions?
What are the biggest challenges you had to face when you started to use Akka in your project?
So the question is, what are the biggest challenges? You mean for me, or what I see in others?
For you and your team.
Right. For me, it was really to unlearn what I knew about threads and locks and thread-based transactions and thread locals and Spring. So Spring has served me and a lot of others very well, but it sort of put me in a mindset where I thought in a certain way, and aspects haven't made that easier. And I had to completely forget about all of that in order to make the actor systems as simple as they could be. So it's really a different way of building systems that unfortunately you can't really reuse many of the bigger patterns that you're used to from writing a thread-based application. And there are some good books I can recommend on what alternatives are there, and one of them is by Vo Vernon, and it's called something with writing reactive actor-based applications or something. If you look it up, then that's sort of like a nice recipe pattern book where it says, okay, if you wanted to do this in your thread-based world, this is how you would do it with actors, and it's sort of a nice reference to get started. Anything else?
Are there any cases that you know of where it would be a really bad idea to use actors in a system where it wouldn't be advised?
So the question is, when would you not use actors? And I think the answer to that is fairly simple. If you look at your actor code, let's take our chat actor again. Damn it, where is it? Here. So if you find yourself having your actors or the main part of your system not having any state here, then there's no point having actors, because the whole point of actors is to isolate state and messages together. So if you have a system that doesn't have that, or you have large parts of your system that don't have any state that you need to remember between invocations, then there's not really a need to have an actor for that, because there's no state. And then maybe you're better off with one of the more the streaming frameworks or something else. Even though Akka has a very nice streaming implementation as well. But I'm not going to go into that today. But use actors when you want to combine state and behavior. Anything? Yeah.
Why did you choose Java instead of Scala?
That's a good question. So the question is, so Akka is written in Scala, and the question is, why did you write this in Java instead of Scala? And it's not because I like Java better. The simple answer is that. Right now, I have a fight, a challenge, or sort of a mission you could see, which is to convince others to use event sourcing rather than the one database with Spring. If I also say, okay, and you have to write it in Scala, I suddenly have two fights. which is, oh, you have to learn this other language, which has a lot of good reasons and a lot of things done well, but it has its learning curve and other things. And by the way, you're also going to write the stuff using a different architecture. So, and picking between those two, I kind of found that at least for Tradeshift and for the context that we're in, it's more important that we get the architecture right, that we get the language right. Having said that, because everything you're doing here is about writing immutable objects and handling your state in a correct way and writing stuff in a lot more functional style than you're used to, and you couldn't do this without having lambdas in Java 8. I do expect people to sort of recognize these patterns and easier roll into Scala or whatever language we end up in as we go down this road. But one of my colleagues actually said to me the other day, yeah, but if we write our code like this, we're basically writing Scala without writing Scala. And that's sort of what you find yourself in. So, all right, you can find me later on. I guess we have to wrap it up here. Thanks a lot for coming.